Hello and welcome back. And in the previous video, we saw that we had to reshape our training data. So why we reshaped that we are going to discuss in today's video. And apart from that, we are going to discuss two more concepts. One is normalization and the other one is the loss function. So we will see the significance of normalization and the loss function along with their basic introduction. Okay, and we will be covering feature scaling and normalization techniques. What are the normalization techniques which are used? All those things we are going to discuss. But before that, let me introduce you one real life example with the help of which it will be really easy for you to understand these concepts. Okay, so I have taken a real world analogy here. So you have to imagine a recipe with ingredients of vastly different quantities, like 1 cup flour versus 1/4 means teaspoon salt. Okay. So if you don't adjust the quantities, the flour dominates the flavor. Okay. So suppose you are trying to make some cake. Okay. And while making that cake, you are using flour and the salt. If you are not able to adjust the quantities, if you don't adjust the quantities, then the flour, like you have taken 1 cup of flour, then the amount of flour, the quantity of flour, not amount, the quantity of flour will decide the basic taste, the test of your cake. Okay. So we have to balance this. How we have to balance it? We have to balance it in such a way that we get the desired cake that we want to prepare with the taste that has been required, that has been requested by your children, or you have said it for yourself, like I will make a cake with mild sweetness, or some kind of uh, having more flour and less cream. All these things, we have taken only two features here, the flour and the salt, but there could be many, right? So we have to balance those features. We have to scale that features in such a way that all the features which we have taken, like the flour, the salt, all these features which are contributing to the taste or the final product, which is the cake, right? All those features which are contributing to the final product, they are equally participating to the model, or you can say to the cake. Okay. Since we are talking about the machine learning model, so as analogy, I have taken the word model here, but yeah, it's all about from the real world example where we are trying to make a cake. Okay. And there is another analogy here. If we are predicting the price of a flat in a society, then there are various features like the area, the carpet area, the number of bedrooms, the number of bathrooms, the balcony, how many balconies are there, what is the balcony area. All these things will contribute equally to the price of the flat, right? But if we have got the training data, suppose you have a kind of data which contains that those kind of features where the values are not fitting to give the correct correct value of the price of the flat, right? Somewhere without the balcony itself, the price is coming equal. Somewhere without the area, without the number of bedroom consideration, the amount is coming same, or there is a vast difference in amount if only one balcony increases. So if we are able to see that the number of balconies is not playing a role while deciding the price of the flat, then in that case you can understand that balcony doesn't need to be taken into account while calculating or while preparing a model to predict the price of a flat, right? Because if suppose you have taken a piece of data, and in that data, everywhere wherever you have found, like there is 3 bhk flat and there are two balconies everywhere, somewhere there are three balconies, somewhere there is no balcony. But in spite of balconies having there or not, if all the flats with 3 bhk, if they all are having the same price, then would you like to consider the balcony, the number of balconies? Would you like to consider this feature which is known as balcony? Obviously no. So you have to arrange your data. You need to remove all those features right, which are not contributing, or you have to arrange the data which have been provided to you in such a manner so that every feature starts contributing equally, right? And even after that it is not able to contribute equally for some of the features, then obviously that feature is an outlier, right? You need to remove that particular feature, right? So I hope with this real world analogy you will be able to understand what we are trying to understand here. We are trying to understand here that the data, the training data that you have got to train your model so that it can predict something is really important, and you need to arrange that data, or you need to normalize that data. That is the keyword, normalization. You need to normalize that data, or you need to arrange the features and the respective values under those features in such a way that every feature is contributing equally to prepare a prediction model. That's the purpose of normalization, which is one of the topics that we are discussing in this video. Okay, so let's come back to the our topics. Okay, so first one is reshaping, right? So reshaping doesn't have a very hard understanding here. You will not find it hard to understand it here, because every library that we are using here, like TensorFlow or the Keras library, all these libraries expect the input data in a specific shape, like batch size, height, width, and channels. You must have seen all these things in your code, right? So there are number of things here. Like if you see on the top, if you see the piece of code, then you can see, yeah, here you can see that it's all about the reshaping. Like batch size is 60,000, then width, height, and then you have to divide it with the 255.0. Why? Because we need to have the data somewhere between 0 to 1, right? So that all the values are very much nearby. Because if you will take the data like 32, 1, 2, 52, 55, then all the columns having that kind of data, where one column data will be dominating some other set of data, right? Because there are different batches. There could be different batches of data where the data may be between 1 to 0, 1 to 10, and there may be data between 242 to 55, right? So there will be different batches of the data, which will not be, which will be confusing the model while we are training the model, which it will be confusing our model. So we need to arrange the data in such a manner so that all the data points, they come into a specific range, so that all the data points or all the features have the equal importance, or you can say have the equal say while predicting, or while preparing a training model. Okay, these things I have already discussed, so I'm just going to pass through it. Okay, so let's come back to reshaping, and I hope you understood the reshaping, because these TensorFlow and the Keras, these libraries are really working on the batch sizes. So that is why we have to reshape that batch size, height, width. There are different, different features. And then there is a channel. Channel means what is the color range, right? Is it grayscale? Is it black and white? Whatever, right? So channel means grayscale, black and white, whatever channel you are using for coloring your images. Okay. Then comes the normalization. We have recently discussed the concept of normalization just before the reshaping. Okay. So what does reshaping do? Okay. Neural network typically performs better with normalized input data, right? It is very much obvious that why it will perform better with the normalized data. Suppose you yourself can consider yourself, you yourself get some data, and based on that data, if you have to provide some kind of analysis, right? You have to predict something for the future. Suppose you get some sales data, and that sales data is very much, not making any sense. Some of the data is really making sense, and there is some batch of there are some set of rows which are making sense to show some common pattern, but there are some rows which are not showing any common pattern. They are way behind or way ahead of the common pattern that you are able to identify with few of the rows, right? So in that case, it will not be easy for you to predict. You will be having like if that happens, if that happens, if X happen, then this could happen, something like that. You will not be able to say anything with surety, right? So even you, the best machine learning model, we are the best machine learning models, right? The humans are the best machine learning models. But even we will not be able to understand, the pattern correctly if we don't have the, normalized data, right? So what does normalization do? Reduces the effect of feature scaling, right? What is feature scaling? Feature scaling is something like, if we have different units, right? If we have different units of data, like for one feature, we have age. The other feature is the income. So the income is like in the thousands, right? 80,000, 90,000. But in case of age, it is between 0 to 100. So the range of data for the age feature and the range of data for the salary feature, both the ranges are differing a lot, right? So when the model, our machine learning model will work on to find out the best pattern to train itself, then in that case it will get confused. It may be confused because all it works on is data. It's only data on which it works on, and it doesn't have that kind of intelligence that we have. That is why we have to do the feature scaling, and feature scaling means you have to adjust different measurement units like inches, feet, miles. The same thing like age and salary. Both have different range of values to a common scale, ensuring all measurement contributes equally to the calculation. I hope you are understanding how it reduces the effect of feature scaling. Okay, now comes the second one, which is really important. It helps with convergence during training. Convergence means, removing that kind of data which is not contributing equally, removing those features which is not which is making it confusing or making it tough for machine learning model or even for you to predict something. So all that data which we are removing, if that data is helping me to slowly reach out to the good conclusion or the good prediction or not, this is known as the convergence, right? Suppose we were talking about the balcony when we were predicting when we were trying to see the prices of the 3 BHKs, and we took the example like, there may be that when the prices were presented to you, the balcony number of balconies were presented there, but still, whether the balcony is present or not, whether there are 2 balconies, 3 balconies, you are always getting the same price for 3 BHK. In that case, balcony is not playing any role. So you will remove the balcony. So after removing the balcony, you can be you can be sure now, you will feel a sigh of relief that yes, now this particular column or this particular feature which is not contributing to the prediction model, that has been removed now, right? So that has been removed. So with after removing that particular feature, you will be converging to the best possible results, right? So convergence is like finding the lowest point in the landscape. So this line, convergence is like finding the lowest point in the landscape, is nothing but it's just like finding the best set of training data so that we can predict it better. We can prepare a model which will be predicting it better. Okay. So this line may be confusing to you, but yeah, I mean, this could be like what it has been written, but it's nothing. It's just like, hey, deciding that kind of data or deciding those features, having those features in your data set, in the training data or test data, so that you have, a kind of data set which is helping the data model to train itself to give the best possible results when asked to predict something. Okay. So what it does, the model navigates the landscape, the loss function. Basically, this is another key point, like loss function. So how does model navigates to the landscape? How it finds out, like how I need to adjust the values of the columns, or how I need to remove the values of those columns which are not useful for me. So all those are generated using the loss functions. We will discuss that in detail in coming videos, but yeah, we have to understand as of now the machine learning concepts in a layman terms, so that even if you don't know the basic mathematics, or even if you don't know that kind of mathematics which is usually used, right, while working on the machine learning model, then also you are able to make an understanding, and then we will go to the mathematical part. Okay, so here the loss function we will discuss, but yeah, before that we are going to see that what are the different normalization processes or the methods which we use. So we have already discussed enough about the normalization, so I'm not going to go into much detail. So I'm just going to iterate whatever has been written here. So in machine learning, normalized data refers to the data that has been scaled to a standard range so that all the feature data falls between 0 and 1 to prevent differences in scales among features. Got it? I think we have enough discussed, so you must have got it. If you know, if you have not got it, you can just give me the feedback. So why we need normalized data? It prevents feature dominance. What do you mean by feature dominance? Feature dominance that we have to ensure that no single feature should be dominating the model due to large ranges, right? I hope it is understandable and it's really easy to understand. Then the second one is improves model interpretability. Normalized features make it easier to understand relationships. You will be easy able to understand like what are the relationship between the two different columns. Enhance algorithm performance. Many algorithms like neural network and SVMs, they converge faster. They have these algorithms, they have the capacity to converge faster. I mean, they can calculate the loss function, and after the loss function they can calculate the ideal function or the ideal equation which will be predicting the model, which will be predicting the values, the output values. They can really do it faster, right? So that's why after normalization, if you have normalized data, then on the normalized data they easily do these kind of things. They easily converge. Reduce risk of overflow. Normalization avoids extremely large or small values. The same thing, like either it should not be going lower side, or it should not go to the very higher side. Like it may be that some person's age is 18 19 years, and some other for the same person the salary is all around 2 lakhs, or 2 millions, whatever, right? So in that case it becomes the issue of overflow. So normalization avoids extremely large or small values, so it reduces the risk of overflow. Okay, so how many types of normalization are there? So this is one method, min max scaling, where we scale the data between 0 and 1. How we do it? X minus min, max minus min. So you find out the minimum value from the data set, then you find out the maximum value in the data set for a feature, and then you find the minimum, and then you apply this formula. Similarly, standardization is there, which is known as the Z score normalization. So you use the Z score normalization when you want to scale your data to between mean 0 and standard deviation 1. So all these are the mathematical terms. I'm not going to explain them as of now here. So it's like x minus mean upon standard deviation. So all these you can calculate for your data. So all these things are done already by your Python packages, right? You don't need to worry about that. All the keras, pandas, all those libraries, right? TensorFlow, they are all capable of doing all these things. Okay. Then we have the log scaling. Log scaling is another way of normalization, and it is useful for the skewed data. Skewed data refers to a data set whose distribution is asymmetrical, which means suppose at some point in your graph, suppose you are plotting a graph with the data points, and at some point or at some specific area, most of the data points are lying, but on the other hand, there are some places on the graph where the data point density is very low. It may be like 1 or 2 data points only they are lying at some point on your graph. So in that case, if your data if the nature of the data which you are analyzing, if the nature of that data is like that, then in that case you use the log scaling, right? So you need to find out where these kind of data you are able to find skewed data. So you can simply go and Google that, right? Like what is the example of the skewed data? You can go there and you can find it out. Then we have robust scaling. Robust scaling means we have to remove the outliers. Outliers are the data points that significantly deviate from the norm or pattern of the rest of the data. Like in the example of the balcony, when you are trying to predict the model, predict the price of the flat, then in that case, balcony was not playing a role at all, right? So that is basically outlier. So balcony is an outlier because of some other reason, but there may be outliers which are outliers because of some other reason. Suppose one example is there, like we are studying, we know that lot many people are suffering from diabetes, right? So normally the diabetes happen after 40 years. Normal range is like after 40 years. So there may be data with you, right? There may be some data with you where you have the diabetes patient data, and that data is basically showing you that there are few patients whose age is between 40 to 60, and I mean after 40 you will be able to get some data regarding diabetes. And if the if the data is also about few of the people who are not in the range of 40 to 60 or 40 to 80, it may be that there are few people who are in the range of 25 to 30 or maybe 25 to 40. They are also getting diabetes. This is also possible, right? So you will be able to find some kind of batch where people between the age group 25 to 40 are also having the diabetes, right? But maybe there could be less data, but there will be some data, right? There could be many reasons, because most of the women deliver the babies around the age of 25 to 30, right? So in that case, it may be that due to the gestational diabetes, the diabetes has been recorded for the ladies, right? So there will be some data. I mean, enough data will be there, but there will be some kind of data while collecting where the children, like between age 5 to 10 years, or maybe the newborn babies, they could have some kind of diabetes, but that is really a very, very less data. I mean, it will be negligible, right? It will be negligible, right? Almost negligible. So in that case, the data point related to the children, that will really not be playing any role. So that data will be considered as an outlier. So I hope you must have understood what is outlier and how the outliers are found. This is the equation, x minus median upon q3 minus q1. So you can understand it from after doing the Google about the robust scaling, what are the outliers and everything, because the mathematics behind it, that is not really important, because this is already done, and this has already been done, and there are functions in the Python packages which are really helping you to do the things for you without understanding the mathematics behind it. Okay, so you just need to understand the concept related to the data management, or you can say the feature scaling. So this is called the robust scaling, the other method, which is the method of normalization. And here I have given example like how the min max, like here you can see like age is 25 but income is 50,000, right? So 30, 60,000, 35, 70,000. So you are going to do the min max scaling. Okay, so if you do that, then you will be able to find the values between 0 to 1. So all the values are very closely associated now, right? So now it will be really easy for the machine learning model to prepare a prediction model, right? This is Z score values. Here you can see for the Z score we have done like this, x minus mean upon standard deviation. So after that it has got this value. So you can see like minus 1 to 1, all the data has been arranged. Okay. So what are the best practices? Normalize data before splitting into training and testing sets. You need to normalize your data before splitting it into the training and the testing set. Use the same scaling factors for both training and testing data. Be mindful of outliers, sensitive normalization methods. Okay, so these are the best practices you must need to think of. By normalizing data, you ensure that features on the same scale. Algorithms converge faster. Obviously, it will converge faster because you have the data on the same scale now. Model interpretability improves, right? Whatever it want to interpret, the model, whatever it want to interpret, it will be easier for it. It will improve. Okay, so now we come to the other topic, which is the loss function. So this is really easy to understand, right? So loss function analogy, it has been given here. Like imagine you are a chef trying to create a perfect recipe for a delicious cake. You have a vision of ideal cake and you want to minimize the difference between creation and that vision. So whatever cake you want to make, you want to less deviate from that vision, right? So what will be the loss function? if we talk about the loss function, then it will be the cake disappointment. I mean, after actually preparing the cake, how much you are disappointed. You were thinking of some other kind of cake, some cake which is really, kind of awesome, but you disappointed after making it, that you didn't even get closer to that kind of cake which you wanted to make, right? So the disappointment, you can consider that the level of disappointment is the loss function. So if you have that disappointment, like how much I deviated, then that is considered in the layman terms a loss function, right? Your loss function measures the disappointment or error between your current cake and the perfect cake. I mean, the model's prediction and your perfect cake, which is the desired outcome. Okay, so I hope you must have understood the analogy. This is very simple. There is nothing like anything which is making you confused here. It's really simple. Now come to the type of loss function. How many loss functions are there? One is mean squared error, right? It measures the average difference in cake texture, flavor, and presentation. So this will be the average difference. Mean squared error is the average difference in the cake texture, flavor, and presentation. Then the cross entropy loss. What does it mean? We will understand all these things in the coming videos when we will see the mathematics around it. Okay. Then comes the cross entropy loss. It measures the difference in cake type, like chocolate versus vanilla, or you can see, like, I wanted to make this category of cake, but I just made something else, right? So this is all about deciding the category. And then the absolute error, which measures the total difference in cake quality. In all senses, how much we have deviated from the ideal cake that we want to make, that is known as the absolute error. Now, after you have found out like what is the disappointment, then what you will do? You are going to do the optimization. Optimization means recipe adjustment. To minimize the loss function, I mean, to minimize your disappointment, you will adjust your recipe model parameters through ingredient proportions, cooking time and temperature, mixing techniques. Mixing techniques means optimization algorithms. Cooking time and temperature means hyperparameters. Ingredient proportion means weights. Okay? Weight means what feature have the bigger weight. Okay? Then comes the convergence. What does convergence mean? I mean, conversion means like you need to converge towards a perfect cake. So if you have to converge towards a perfect cake, then in that case you have to iterate it again and again. So as you iterate and adjust your recipe, your cake disappointment or the loss decreases. When you finally achieve the perfect cake, your loss function converges to its minimum value, right? When it reaches to it, minimum value, then there you go. You have the best prediction method, or you can say you have the best cake, right? And then comes the concept of overfitting. Overfitting means you have created over decorated cake. If you over adjust your recipe, your cake becomes too specialized. I mean, it becomes overfitted. You are preparing a vanilla cake, but it looks like something else. If you are doing overfitting, maybe it's altogether a vanilla cake, but it's still the kind of toppings you have done, the kind of decoration you have done, that is making it looking like something else, right? So overfitting, you have to also take care of, like, you need to be away with it. Okay, you need to take care, like, you need to just get away from it. Okay, this analogy illustrates how a loss function measures the difference between predicted and desired outcomes, guiding the optimization process to achieve the best possible results. Okay. So prevent feature dominance. This we have already discussed, how it prevents the feature domination. So that all is the concept, basic concept. The mathematics that is done behind it, that we are going to discuss in the coming videos. So I hope you must have understood this video and this lecture, and in the next video or in the next lecture, we are going to meet you soon again. Till then, have a nice day and